A warm welcome and namaste to all of you for this lecture on mathematical foundations for machine learning. In the last lecture we looked at the idea of fields, and using the field we defined the idea of we conceptualized the idea of vectors and vector spaces. We saw what are all the properties that a vector space has, and we also figured out how to construct vectors using the field elements, that are also something which we saw, and field operations. And when we understood the idea of vector addition, scalar multiplication, etc., we kind of stopped the lecture with this question on some examples for vector spaces. And in the context of machine learning, what would all these things boil down to? This is what we stopped in the last class. And in today's class what we will do is, like, we will look at some examples for vector spaces. And what I propose to do is, like, the 4 classes we will do the idea of math, and probably the last class that we have for a week we would try to converge all that we have covered in the 4 classes with in the context of machine learning. Okay. So what we will do is, now we look at some of the examples of vector spaces, and then we will look at subspaces, and we will see some combinations of vectors and so on. So that will be the agenda for this class. Okay. So some examples of vector spaces. So what are the properties that this vector space must hold or must obey? We said that a non-empty collection defined over the field with operations plus, that means vector addition, and multiplication, which is scalar multiplication. This non-empty collection should be such that if you take any 2 elements from this collection and add them, the resultant must be an element of this collection. If you take a scalar from the field and then take a vector from this collection, the scalar multiplication of this vector from the vector space must be resulting in a vector which is also an element of the vector space, and then we said there must be this 0 vector present in the vector space, right. So that is the idea that we had. So what is the smallest, what is the simplest vector space that we can have? Remember, we defined the vectors over the field R, and that field over the field F, and that field F had all these properties that we actually spoke of for vector spaces. It was closed under addition, it was closed under multiplication, and the 0 element was also there. Therefore, the simplest vector space that you can look at is basically the field itself. So the first one that we have is, basically field F itself is a vector space. You can check, as I mentioned, you can check all the properties of vector space have actually been taken from that of I mean the field, in the sense your vector addition was basically component wise addition, that means you were adding field elements, that means the closure is already there, closure under addition is already there. When you looked at scalar multiplication, you had one element from the field, that is the scalar, and the vector component, each component is also going to be from the field. Therefore you are doing basically the field multiplication over there, which means it is closed under I mean the field is closed under field multiplication, and you also had this additive identity element which was the 0 which was there in the field. Therefore the field itself is a vector space. Then the second one, we say that any Rn, I would say Rn for any n, let me put it that way, that would be better. So Rn for any finite n in fact you could also have countably infinite n also. So Rn for any finite n or for any n is going to be a vector space. over R. So, you can have R2, that means your xy plane, you can have R3, the 3 dimensional space, and so on, all of them would be vector space, because you take any 3 component vector and add another 3 component vector, the resultant is going to be a 3 component vector which is going to be in the 3D space. Take a scalar and then multiply any 3 component vector, that resultant is going to be another 3 component vector in the 3D space. You already have an origin there which corresponds to the 3 component 0 vector, therefore, that would form a vector space. So, you can define that way. The third one is most interesting one, we are going to say that look, third one is set of all polynomials of degree less than or equal to n and with coefficients real is a vector space over R. For example, you take n is equal to 2, that means you are going to look at set of all polynomials of degree less than or equal to 2, which means it could be a constant, it could be a degree 1 polynomial, or it could be a degree 2 polynomial. If you add 2 degree 2 polynomials, you are going to get either a degree 2 polynomial or a degree 1 polynomial or a 0 degree polynomial, which means that all these types of polynomials are included in this set, therefore, it is closed under addition, vector addition. You take any scalar and then multiply any polynomial of degree 2 or less than that, the resultant is also going to be a polynomial of degree 2 or less, therefore, it is closed under scalar multiplication. Since you said degree is less than or equal to n, if you have the polynomial to be equal to the 0 degree polynomial and have the 0 vector is also present, therefore, this set of polynomials of degree less than or equal to n would actually form a vector space. We also have this set of all square matrices over R. Okay. Set of square matrices, let us say n by n square matrices, okay, of dimension n, anyway it is taken care. Set of square matrices over R would be a vector space, it would be a vector space, because you take any 2 square matrices, add them, resultant is going to be a square matrix. You take a scalar multiple and you take a constant k and then multiply a square matrix, all the elements of them gets multiplied by this k. So, resultant is yet another square matrix, and the square matrix which contains all the elements to be 0 is also a valid square matrix, and therefore, we are going to have set of square matrices over R to be a vector space. The fifth one, we are going to have set of all let us say real symmetric matrices, over R. Anyway, I put it as real symmetric matrix, so it is going to be over R. So, this would be a vector space. You take any 2 real symmetric matrix, add them, the resultant is going to be a real symmetric matrix. Scalar multiple is going to be a real symmetric matrix, resultant real symmetric matrix, and matrix which contains all the elements to be 0 is again a real symmetric matrix. So, that set of real symmetric matrices a vector space. You also have set of all continuous functions, set of all continuous functions of time t, functions of time t let us say for t in minus infinity infinity defined over R. These are all examples of vector spaces, right. These are some examples of vector spaces. You can prove each of them. I mean, like I have listed, I mean I have also indicated as to how to prove them. So, you would see that whatever list that I have given here, they all form that individual collection would form vector spaces over R, right. Now, let us take a simple example. Consider R2. Consider R2. So, what are we going to do? Basically, I am going to look at the xy plane or the x1 x2 plane. So, let me call this as x1 and let me call that as x2. So, this plane I am going to look at. Instead of looking at all the points in x1 x2, I am going to look at a sub collection of this point. That means I am going to look at a subset of points, a subset of R2. Now, what is the subset that I am going to look at? I am going to look at a subset of R2. Let me call that as say S1, which basically is of the form, let us say x1 comma k x1, where x1 is real and k is also real, right. I am going to have x1 comma k x1. This is what I am going to have. So, what we will do is I will actually, instead of making it as S1, let me call that as Sk, and I will replace for every k that I get, I will replace that corresponding index and then see what is the geometry of this, and then we will probably understand a bit better. So, for example, let me take k is equal to 0. So, therefore, I am going to get S0. The set S0 is going to be the set of all vectors of the form x1 comma 0 into x1. So, that is going to be 0. So, I have x1 in R. Now, how does that going to look like? So, how does that going to look like? This is going to be this entire line, which is basically my x axis, right. It is going to be my entire x axis. This is corresponding to, let us say, I will call this as S0. This entire set is basically my S0. Now, what is interesting, you take any two elements in S0 and add them, the resultant is also going to be along the same thing. Say for example, let us consider, let u comma v be an element of S0. What does this mean? The vector u is of the form u1 0 and the vector v is of the form v1 0. Now, what we have is, I want to look at u plus v. U plus v is nothing but u1 0 plus v1 0, which is nothing but u1 plus v1 0 plus 0. This is going to give me say u1 plus v1 and 0. This is also an element of S0 because it also has the same structure where the second component is 0. So, this has the same structure, that means u plus v is an element of S0, therefore, S0 is closed under vector addition. Right, epsilon is closed under vector addition. Now, let me take some scalar, let us say alpha. For alpha in R, I am going to look at alpha into, let us say u1 0. I am going to get alpha u1 into 0, which is also an element of S0, right. This is also an element of S0. So, we see that S0 is closed under scalar multiplication. It is closed under scalar multiplication, and we also see u1 is equal to 0 is a valid point here, which is going to be this origin. So, this is also an element of S0, therefore, we see that S0 is closed under vector addition, scalar multiplication, and 0 comma 0 is an element of S0, therefore, S0 is a vector space over R, is a vector space over R, right. Now, what I am going to do, let me change my, let me have this. So, let me do this. I had S naught to be this. So, this was my set S naught. Now, what I am going to do is I am going to look at Sk. This is what we said, the set of vectors Sk is nothing but x1 comma k x1, x1 and k in R. So, now what I am going to do is I am going to look at S1, that means k is equal to 1. I am going to look at, let us say x1 comma the set of all vectors of the form x1 comma x1 where x1 is in R. So, how does that look like? That basically looks this way. It is the 45-degree line that we have, right. This is along, this is basically the 45-degree line. Let me first draw this line. This is basically the set of points that I am going to have S1, which is of the form x1 k x1, right, that is what we are going to have. Now, I am going to take two vectors here u and v, u is equal to u1 comma u1 and v is equal to v1 comma v1. So, we have u plus v is equal to u1 plus v1 comma u1 plus v1, which means the first and second components are the same. Therefore, S1 is closed under vector addition. We can also see that for say some alpha scalar, we have alpha into u1 comma u1 is equal to alpha u1, which implies the second component is the same as the first component. So, this is S1, therefore, S1 is closed. S1 is closed under scalar multiplication, and I have 0 comma 0, both components being the same, is also under is element of S1, which means S1 is a vector space over R, right. So, this is also a vector space over R. Now, I am going to take the third one, let us see if we can get something interesting out here. So, I am going to look at S minus 1. So, what does this mean? S minus 1 is basically the set where we have x1 comma minus x1, where x1 is R, right, x1 comma minus x1. So, what does that mean? If you take x1 to be minus 1, x2 is equal to plus 1, x2 is equal to minus 2, then when x1 is equal to minus 2, x2 is equal to plus 2. So, we are going to have a line which is going to be like this, right, that is that 135 degrees line that you have. So, it is going to be like this x1 comma minus x1, and what we see here, you can prove that, you can actually prove that this guy is also a vector space over R. We can prove that, you can try, S minus 1 is also a vector space over R. Similarly, you can do S2 where x1 comma 2 x2, S3 to be x1 comma 3 x3. You can do a whole lot of stuff, and you will see that the locus of all the points that you have along this x1 comma k x1 would always be a straight line passing through the origin. Therefore, we are going to make a very interesting observation here. We are going to say that any line passing through the origin is a vector space over R, is a vector space over R. right. I mean, so geometrically you find that okay, I mean the vectors are all in the same direction. So now what you do is you add them, the resultant is going to be along the same direction and so on. So we see that any line passing through the origin is a vector space over R. But what is interesting is the moment you take any line passing through the origin, this line does not contain all the points in R2. We already started saying that look, I want to only consider the subset of points from R2. In fact, you could even have this, what is that, you could even have this guy 0 comma x1, you could even have this, that means my y axis, that is also a line passing through the origin. So what is interesting is all these fellows do not contain all the points in R2, but then they just contain a subset of points in R2, and this subset of points have all the properties of the vector space R2. Therefore, we are going to make a nice statement here, we are going to say that any subset of a vector space, we are going to make this any subset of a vector space which by itself is a vector space with operations, let me just make this any subset of a vector space V, I will put it that way so that it does not confuse. So, any subset of a vector space V which by itself is a vector space with operations as defined in V. You give a name for this, is called a vector subspace of V. Okay, it is a vector subspace of V. Now let us consider two more examples and then probably see if we can make some interesting things. So the first thing is, note every set is a subset of itself. Therefore, any Rn is a trivial subspace of Rn. Let us look at the second one. Consider this set which I will just call this as theta naught, which just contains the origin. Now if you look at this set which just contains the origin, at least I am looking at R2, I mean you can look at origin in Rn, not a problem, the 0 vector in Rn, not an issue. I am going to consider this subset theta naught. Now if I take the element from theta naught which is the 0 vector and add it to itself, I am going to get the resultant to be 0 vector. Any scalar I am going to multiply with the 0 vector, I am again going to get the 0 vector, and the 0 vector by itself is there, the only element of the set. Therefore, this is a subspace, this is also a vector space, and this is also a subspace of, let us say, R2. That means the set containing only the 0 vector is a vector subspace. So let us generalize this, the set containing only the 0 vector only the 0 vector. 0 vector here implies all components 0. So the set containing only the 0 vector is a vector subspace, and this is also a trivial subspace. It is a vector subspace, trivial subspace. Now in a higher dimensional space we are going to make the statement, let us say in any Rn a plane passing through the origin is a vector subspace. Right. So, this is there. No. So, the question is, why would we want to look at this idea of vector subspace? Why are we not just happy with looking at a vector space and then leave it like that? Why would we want to look at the idea of vector subspace? When you look at I mean this also comes for example, you look at the set of integers. What to do is I want to partition this integers basically into something which is a set of odd integers and the set of which are not odd integers, basically the even ones. Basically these subsets or the subspaces help you to partition your vector space. We will see that when you do linear transformations, what are all the subspaces associated with the linear transformation and so on, which is very essential as far as your machine learning is concerned. We will look at all that. But geometrically you have all these ideas like a line passing through the origin itself, or a plane passing through the origin, or any linear geometry that passes through the origin would always be a vector subspace. Now the questions that we have, there are a few questions that we need to answer here, which we will try to look at right now, and probably will answer those questions in the next class. So the questions that we have here, some questions. Question number 1, what happens if we add multiple vectors in a vector space basically instead of saying add just multiple vectors, let us say in other words the question that I am asking is like, what is it to say combining vectors? What is it to say combining vectors? Second question that we have is, suppose we want to transform an entire vector space what is the strategy to study the effect of the transformation on the entire vector space? So these are two questions that we would want to answer. One, so how do we combine vectors? What is it to say combining vectors? How do we combine vectors? So this is first question that we want to answer. The second question that we want to do is, in any vector space you take, you are going to have infinitely many number of vectors. So the question that we ask is, suppose I want to transform the entire vector space, right? I want to transform the entire vector space. how do I know what will happen to each vector in the vector space? How do I study this? So, what is the strategy that I need to employ to study the effect of this transformation on the vector space? That means I want to study the effect of this transformation on individual vectors in the vector space, each and every vector in the vector space. So, what is the strategy that I need to adopt? In a sense it's also something like this. Remember when we had the pandemic that was there, everybody had to be given vaccine, but it is not that you directly give vaccine to everybody. Instead you wanted to study the effect of the vaccine on the entire human race. How did we go about doing it? Can we adopt a certain similar strategy here? That means can we choose certain fellows or certain people in the population and then see what is the effect of this vaccine on these people, and therefore say what could be the effect of the vaccine on the entire population, human population. Can we do something similar to that here? And that is where we get into the idea of basis for a vector space. And in the first question, to answer the first question, we are going to look at the idea of linearly combining the vectors, and this would be the focus of the next lecture. Thank you.